In the previous video, we created a linear regression model. Now, there are some assumptions that come with a linear regression model. The first is that we don't have any multicollinearity. Multicollinearity is when your predictor or independent variables are highly correlated with each other. So we're assuming that whatever variables we're using to predict, in our last video, we're predicting earnings per share, that they are independent of each other. And if they are not, then the problem is trying to figure out how much impact each variable has when those predictor variables are moving together. And so we can likely see that in our earnings per share data, they're using the same data or the same financial statement to calculate a number of different ratios, often with the same underlying calculations. And so because of that, right, we might have multicollinearity. So we have to consider how independent are these variables of each other, and we can do correlation calculation to see if our variables really are independent. So we would need to check that. The other thing when we're looking at our linear regression is that we're assuming that our residuals are independent of each other because our variables are independent of each other. And we're looking for models where that residuals or measurement error look like random scatter. If they have some kind of pattern, then we have chosen the wrong model. So for example, if we do a linear regression and we're seeing a pattern here, we might need to have more of a polynomial or a model that takes into consideration some kind of the cycle or seasonality to it. So there are things we assume with a linear regression and we can check to make sure our model is better. We are assuming that the residuals are normally distributed. And when you have a single linear regression, one predictor variable, you can create a QQ plot. That's kind of what my face is covering up. And what this looks at here is that if your data is kind of close to along this 45-degree line, then you have a normally distributed residuals or measurement error. If we have a significant curve here, then we don't have normally distributed error. So measuring whether or not our linear regression model is appropriate. We also assume that we have constant variance. So when we look at our residuals, our measurement error, it should look like random scatter. It should not have this, what you see here. This is heteroscedasticity, where the variability is increasing with whatever this variable is here. Our error is increasing rather than it being just random. So homoscedasticity is constant variance. So when you look at your data, it should be randomly scattered. So if we look at what we just did here, when we look at this particular residuals or error from this linear regression for our earnings per share, we have some outliers that are skewing the data. We'd want to go back and look at what is this data and is this an error? Maybe there is a typo in the data set that is making it an earnings per share that's really not even possible. That's causing an issue here. We're looking at this and we don't seem to see like a pattern, right, in terms of a general curve or anything to that here. And we don't seem to see any heteroscedasticity, right? When you look at the variability, that variability seems to be somewhat equal on the left side of the graph with the right side of the graph. Okay, so we've checked those pieces there. Now, when you are creating a model, we have a challenge between overfitting a model and improving the accuracy of the model. When we were doing our forecasting, we talked about overfitting. So for example, actually I'll just show you here. At the very bottom of this sheet here, I'll show you an overfit model. So this is from our forecasting videos, and we used regplot to plot the number of complaints over time, and we had created a polynomial of degree 4. And so remember with a polynomial, if it's degree 4, it could go up, then down, then up, then down. So it fits the historical data really well because it's got every single movement. Well, this is an overfitted model because it mimics every single curve. But the challenge with a polynomial is that in the future, a polynomial for forecasting time series, it only goes up or down. It doesn't actually maintain the wave that you can see in the historical data. So an overfitted model fits the historical data really well and does not fit the future data at all. And so when we're doing our time series, we were concerned with overfitting by choosing too high of order of polynomials. So we stuck with polynomials of degree 2, just up or down, or linear regression where we're looking at just time as our predictor variable. Well, when we're dealing with linear regression with multiple variables, right? So that's what we're talking about here, more than one predictor or independent variable. We also have to be concerned about overfitting. And in this case, the overfitting comes from having lots of predictor variables. So we have tons of variables that then lead us to mimic every single change. Now, so far in the regression examples we've been looking at, if we go back, our R-squareds have been pretty low. So we definitely don't have an overfitted problem. So let's just go back here. Right. We only had an R-square here of 25%. We weren't covering a lot of the variability in the data in these data sets that we've been looking at. So an overfitted model would have a really high R-squared, kind of like we saw with our penguin example, where the variables really covered everything, right? And so when it comes to linear regression, if you have that overfitted model, right, we have that high accuracy for the training data. The challenge, of course, is the low accuracy for the testing data. So we've mimicked everything that could possibly happen in the existing data set, but it doesn't necessarily represent the future. So to adjust for that overfitting, we can do what is called ridge or lasso regression. This only works for linear regression. So if you have overfitting with a polynomial time series, take the orders down so you have less curves, okay? But if you have linear regression that is overfit, so you've included lots of variables, it's represented all the different variability, you can use ridge or lasso to adjust for overfitting without removing a bunch of your variables. The idea here is that some of the part of the variable is important to explain something we didn't have before, but by having so many variables, we do have an overfitted model, which, as we said, can cause an issue of high R-squared if you look at the existing data we use to build the model, but a low accuracy for new additional data points. So to adjust for this, we can use ridge or lasso. The difference between ridge and lasso is that ridge adjusts for the overfitting by making the coefficients smaller. So what we're doing is we're minimizing the impact of some of the predictor variables. So if you think about, like when we looked at, let's go back, the coefficients we found for our earnings per share, what we would be doing is taking these coefficients here and minimizing them each a little bit so that in the model itself, each one is having less of an impact on the earnings per share so that we can keep all of the variables that we have. We have lots of variables, okay? That is the ridge regression. Lasso regression, what it does is it says, okay, we have overfitting because we have too many variables. And so what it does is it actually makes some of the coefficients zero. So it's essentially saying, let's simplify the model by using less of the predictor variables. And we can use this lasso regression if we have sparse data. So if you have data where you have a lot of no values, so not missing information, but if your predictor variables are going to be more binary, yes, no, or whether it's a measurement and a lot of people have zero measurement and then there's a couple that have it. So if we're looking at predicting features, and a lot of them don't have that feature, so the measurement is 0, and then others have a number for that, then you would use a lasso. So it's saying, okay, well, these coefficients have less of an impact. These variables have less of an impact, perhaps because we don't have measurements for everybody, or everyone doesn't fall in those categories. And so we'll reduce the number of predictor variables by making those coefficients 0 for those. So let's look at how ridge and lasso work. So we are going to do this ridge regression here on this data set that we were looking at previously. It's really not the best example because, again, it's not explaining a lot of variability, so it's not an overfit model to start with. And so because of that, the ridge regression is likely not going to do a whole lot of improvement, but we can kind of see how this process works, and then we'll see as well the lasso regression. So if you're working along with us, we are at, back up one step, we are drstephpowers.github.io/BIA, and we are doing regression that you see here. You will also need the fundamentals.csv file, which you can find once you click in there as well. So in fact, if you just ran that particular model with us in the previous video, we have already, let's just go back in time a bit, we have already imported the stock data from our drive, and we have looked at it briefly here. And then what we have done is we have created a reduced version that we'll call here our stock 2. And stock 2 is just the earnings per share, cash ratio, after tax, return on equity, gross margin, and current ratio. We're just going to take those. So these 4 here are going to be our predictor variables, and we're going to try to predict earnings per share. We're dropping the NAs, so where it's missing, we're doing a subset of this data set here because there might be missing information in other columns, and we don't want that to limit the sample size. So we take a subset, we drop the NAs, and then we did a test train where we have split it into 80% for our training and 20% for our testing. So we ran that. And from that, we did our linear model. So if we're going to do ridge regression, so let's say that we had that high R squared, we had lots of variables here, but we are concerned about the difference between being able to predict the past data that we use to build the model versus the future data that we're looking for. You can use ridge regression to reduce that overfitting. So what we're going to do is from sklearn.linear model, we're going to import ridge. We can import the metrics mean squared error and R squared. This allows us to do a comparison because in our previous video, we did find the mean squared error and the R squared for that particular model. So we can see that, can we improve our R squared? Can we reduce the mean squared error in the models themselves? Or at least not make them worse as we adjust for some of the overfitting issues. All right, so we're going to import ridge. We're going to import mean squared error and R squared. The way ridge regression works is that you are going to call the model. It has a hyperparameter that is alpha. And so you would specify that alpha. Recall that for the ridge regression, remember for ridge regression, we're minimizing the impact of the predictor variables. So the alpha is how much we are minimizing that, how much we're making the coefficients smaller. So a larger alpha is going to make the coefficients smaller. So we can start with an alpha equals 2, and we can look at changing that momentarily. So we're going to call the model ridge with our hyperparameter alpha equals 2, higher number making the coefficients smaller. Fit it on our training data, X train, Y train. And then what we can do is we can, excuse me, we can find the coefficients, we can find the intercept, And so here we look at our coefficients, 0.0046, 0.0016. Just go back. So you can see here, these coefficients have not changed a whole lot. Our alpha is a smaller number. We can look at if we change that alpha to a bigger number, does it reduce some of these coefficients? So these other one was 0.01 and 0.001. Let's just take a look here. 0.01. So in this case, we can see not really a big change in the actual data. If we look at predicting based on our test data, we can see the mean squared error here, and we can get our score from our data. Now, the lower the score, so it's just like R squared, right? Higher score is better. And we can see in this particular case number, we're not explaining a whole lot of the variability with the variables that we have. So we can see that the scores remain quite low. We can actually run the score here for the testing data and for the training data. And we do that, right, because what we're trying to do is make sure that we can improve the model both in terms of adjusting for the impact of those coefficients so we're not overfitted, so that we can increase the accuracy on the test without losing too much on the train. So we can see, right, this one doesn't fit particularly well. We already knew that. It wasn't really overfit. You can see the mean square error is essentially the same. Excuse me. Right, so mean square error, R squared, right? You're seeing the same thing. So here we are not significantly adjusting. Let's try making this bigger. Run it again. Okay, remember 0.004, 0.001. Okay, those don't look any different here. Again, not a great data set to show this for just because it's not overfit to start with, so you're not seeing much change since it doesn't have an overfitting problem to start with. But if we did have a model with a lot higher accuracy, a lot more variables predicting it, we would see a change. Now, what you can do is you can use something called Ridge CV, so cross-validation. We've talked about that before. And what this does is it can go through a range of values for alpha. So here we're using NumPy, so make sure you've installed NumPy as NP. And we're going through a range, 1 up to, but not including 100, in increments of 5. So when we do that, you can see here that it goes 1, 6, and so on. Alpha cannot be 0, so that's why you need to make sure that this is not 0 to 100. It does need to start here above 0. And then you can do it in whatever increments you want. And then what we're doing is running that same ridge regression where it's going through and it's using all these different alphas that you have here. So alphas equals alphas, because that's what you called it. And then they're going to fit and train the data. So by calling this with the Ridge CV instead of just Ridge, which we import from sklearn linear model, then what it does is it goes through and cycles through all these different alphas to find you the best model that it can. And then what we would look at here is we would look at, does that change the coefficients? And in this case, they don't change. And the intercept. And then the other thing we would look at is, does it change the mean square error, or R squared? And of course, in this case, there's really no change here. We would check against the training data and the testing data. We could also look at the error. So we can subtract the testing from the predicted here and look at our residuals. As we noted before, what we should be doing is checking for these outliers. Maybe there's a typo here. But again, checking for, does it center around 0? Does it look like random noise and not have patterns to it? Does it not have, as we were talking about before, that heteroscedasticity as we check our assumptions here? So we can use ridge regression. My apologies, the data set's not particularly a good one for this. it to adjust for that overfitting, because we want to make sure that we have high accuracy both in the training and the testing data. What I can show you with this particular data set is the lasso regression impact, and how it works, and we'll do that in our next video.